Yeah, we are live. You can go ahead.
Okay. Yeah, welcome back, everybody. So, welcome to the second lecture. So, we'll continue our discussion on Turing machines and get on to topics like non-determinism stuff later in the class. Just a request, if those of you can turn on their videos, do turn it on if it's fine by your end. It will be good for me to see faces while speaking rather than speaking to an empty screen. Okay. Any questions from last time? So we had sort of defined this model of computation Turing machine and sort of commented about some robustness of this model. We had said that it had this following feature. It had a Turing machine we defined it based on a tuple, which is the number of tapes, the alphabet, the state space, and the transition function. That was the Turing machine for us. The alphabet, we always said it had to contain these four designated symbols: 0, 1, the end of tape symbol, and a blank symbol. And this I will denote as B, the Boolean alphabet. This is any tape, this one guy, but it could have a much larger alphabet too. And we sort of alluded to this claim last time. We'll sort of see a proof of this. The fact that if there's any function f which is computable by a time constructible Turing and a time constructible t, so that f is computable by some Turing machine m in time t, but the Turing machine uses some alphabet gamma, possibly very large gamma. You can actually, without loss of generality, convert the Turing machine from m to another m. So basically, what I'm claiming over here is this is working over the alphabet gamma, whereas this will work over the alphabet t. You can convert. So if there is one Turing machine such that f is computable by Turing machine m using alphabet gamma in time t, then there's another Turing machine m prime, so that f is computable by Turing machine m prime over alphabet b. And furthermore, the extra overhead, let's forget about this. I don't know why I put 4 here. What I meant is some constant times log gamma into t. So the overhead, you get to this one. We'll see a proof of this. This is something I mentioned. That is, without loss of generality, you can always convert the alphabet just to 0 ones. That's one thing. Then we also said Turing machine, we defined it in terms of multiple tapes. And the typical Turing machine had an input tape, a work tape, the last of which was what called the output tape. So always had 2 tapes. In which case, if in this case we allow the input tape to be just read only and all the other tapes to be read write, there is some type of Turing machine called the single tape Turing machine, in which the Turing machine has only one tape, which is its input, work tape, and the output tape. And this is a read write tape. These are what we'll call single tape Turing machines. And the second claim towards the end of last lecture, which I had mentioned, is the following lecture. That is, if a function is computable by a Turing machine t using k tapes in time t, where t is once again a time constructible function, then there's another Turing machine m prime, which computes the same function, but it's a single tape Turing machine. The key thing to notice here is this is possibly a k tape. This is possibly a k tape Turing machine, whereas this is a single tape Turing machine. So you can transform anything from k tape to single tape, and the overhead factor is this quadratic factor. So the original one was Tn. So let's quickly see a proof of this. We already mentioned the proof of the first part. So alphabet reduction. How does one expect to do this? So suppose we have some tape. We already given one Turing machine which has some input tape, some work tapes. This is the Turing machine M. I want to convert it to another Turing machine M prime. So they want it to be M prime. So that M prime, so if this works over the alphabet gamma, I want this to work over the alphabet P. And it's the most natural thing. We'll just encode gamma So M, this is what M prime is going to be doing. M prime is going to be encoding gamma in binary using log gamma bits. So, and so what will happen is as a symbol here, so let's say a symbol here will get converted to log gamma symbols over here. Why does this not change over here? So a symbol here will get transformed over here into log gamma symbols. So whenever it has to write one symbol in the over here, it will write log gamma symbols. It will read. So the way the head will move is to read one symbol. To read one symbol here, it will have to read log gamma symbols over here. Then it will interpret that as a symbol over there. It will expand its state space suitably. Like the state space of Q prime's state space would be expanded so that after reading log gamma symbols, it knows it has read this particular symbol and it will work. It's just the vanilla, the most natural thing which we do. So every action in M just gets converted to, it blows up by a factor log gamma in M prime. Reads this, do this. And because you don't have to do this in the input this one, because the input was already always a function of 0, 1. The input, I'm not changing the input. The input is just 0, 1. The output is also 0, 1. So for that we could handle. The input and the output still work with the 0, 1 output. Okay. So this is fairly simple. What about the other? This one. What about reducing now this proof of claim 2, which is you want to go from k tapes to a single tape. So once again, what's the question we want? I have some Turing machine which has this input tape and say a bunch of tapes of this form. These are its work tapes. That's the Turing machine M. I want to transform this into a single tape Turing machine. TN. M prime. How would you do that?
Maybe like stick them parallelly in one single tape or something. Like it becomes this is tape 1, then this is tape 2, and so on.
Yeah, so the question is, there are two ways of doing it. So there are a few obvious ways to do this. We could say that we'll write the contents of tape 1 first, then tape 2, then tape 3, and so on. So this tape itself will have first tape 1 contents, then tape 2 contents, and so on up to tape k contents. But during computation, suddenly the point is how long is tape 1 content? Tape 1 contents, it's at most. So sometimes tape 1 suddenly you read more. Are you going to go and write more into this? So another way of doing it is sort of, that's one way of handling it. What I'm going to do is actually interleave the tapes. I'm going to interleave the tapes, and write them all on the single tape in the following fashion. That is, I'm going to assume that the first tape is written at symbols 1, k plus 1, k, 2k plus 1, 3k plus 1. These are the places where the first tape is written. The second tape is written on symbols 2, locations 2, locations k plus 2, locations 2k plus 2, and so on. And in general, the kth tape is written at locations k, 2k, 3k, and so on. So the tapes are sort of interleaved. So The first symbol is the first tape symbol, the second symbol is the second tape symbol, the third symbol, and so on up to the case symbol, and then you come back to the first symbol. So in order to read the first tape itself, you have to read one. So how does the work of this, how does this Turing machine work? It's going to have the input. So it's going to have the input. So what it will do is it will call the input comes over here. Do you see my laser pointer? Yeah. What's going wrong? Okay. Here the input. So my laser pointer is not working. So it takes the input. Right. The input is on the single tape Turing machine already. What it will do is it will sort of interleave the input. Now it will sort of spread out the input as if right now the input is all together in one chunk. It's going to spread it out as if the input was every k steps apart. And then to make a single step of the original Turing machine M, way M prime is going to work is going to make one full sweep, read what is there in every single tape. How do you know what is there in every single tape? So every input location, so every bit, every symbol of the original tape, original Turing machine M is now has two corresponding symbols. Two corresponding symbols in the single tape version. That is, if A was a symbol there, A was an alphabet there, there'll be A and A hat will be two alphabets over here. What does A hat denote? A hat denotes is the head present on this location. A is just this one. A is this one. So what's going to happen? The first tape is at these locations. The second tape is at these locations. The third tape is at these locations. Sorry, I should have drawn different colors. Anyway, and suppose I have A, B, C, then D, E hat, F. What does that mean is the head on the second tape. This is the second tape, this one. The head over here is on this position. So because now, so the Turing machine makes one full sweep, the whole thing, finds out where the head is on all the K tapes. At the end of it, it knows where the head. Now it knows how to make the translation. It goes, look at the transition, and then makes a sweep back again. So one single action of the original K tape Turing machine is executed by doing a forward sweep of all the machines and a backward sweep. So a single transition step of the Turing machine M has to be, to execute it, you have to do a full sweep. You have to find out where all the heads of all the K tapes are there. And then once it knows at the end of it, it knows what's the action it is to take. It makes a sweep back and executes the change. It will change the position of the heads. This one, move right, left, and do this. So it's going to be this forward sweep, backward sweep. So a single step of TM M is executed, is simulated by a forward sweep, forward and backward sweep of Tn steps each. So a single step just blows up into Tn. Therefore, the total number of steps is going to be some total number of steps is Tn times this Tn. There's some extra constant, so it's roughly like T squared, and steps is the entire execution is going to take a quadratic growth. Okay. Wanted to mention a couple of more things. Notice that over here already I need to know that T is time constructible. It needs to know how long to go the sweep is. So you're using the fact that this time construct, it needs to go how long this sweep and then come back. It needs to know how this. So it needs to know time. Tn, the Turing machine uses this to compute it and then goes so far, comes back, goes so far, comes back. So
Prahlad, what about the blank symbols? Like, you don't know, right? On the right-hand side, there could be a few blank symbols which might get used up at some point and which might not get used up.
So you always assume, this is a convention that we take. The moment you see a blank symbol, there's everything else to the right of it is a blank symbol. So So you make, so what you do is you take the original input tape n, the original input was n, you have now blown it up. So you take Tn steps. There are some of them are blank symbols. You read Tn in the first block, Tn in the second, so you read k times Tn in one sweep, and then another k times Tn in the next sweep. You keep going back and forth. Tn is a number you know, so you can do this back and forth. So you would be reading blank symbols in this sort of thing. Blank symbols possibly you have blank symbols are replaced by another blank symbol, say blank dash or something on this, and that's how you execute this.
Okay. Anyways, those blank symbols are going to be on the right side, like the far right side or something,
They
right?
will be on the far right. But notice that if with this way of doing it, there are blank symbols to the far right. After KT and things, there are a lot of blank symbols. I'm not going to touch them, but there are also intermediate blank symbols. That is, one tape might not have gone because you interleave the tapes. There will be blank symbols over here. So these blank symbols and those blank symbols will sort of change. Use a special difference between these blank symbols and those blank symbols.
Okay.
Okay, this is a vanilla thing, but why did I do it to reduce it? This is something all of we can see this one. I want to say there's something nice about this simulation. This simulation, want to look at, if you look at it carefully, there's something, look at where the head is. So look at the position of the head of a Turing machine. The position of the head of a Turing machine is a function of what? It's a position of a head, position of the head of the Turing machine. Head on all the tapes. It's on all the K tapes. Here there's only one tape. Is a function of what all parameters? It's first a function of certainly which Turing machine you're working with. Position of head at the ith time, at time I say. Certainly a function of I, and it's a function of with the what input you are working. So certainly it's a function of these three parameters. Where the head is at the ith time is a function of which Turing machine you're working with, what time are you care about this, and the input you started off. Once you change any of these, where the head is, the position of the head on the tapes changes. That's true for any Turing machine. But this simulated Turing machine has a nicer feature than has something better than what I said over here. Can you know, is there a difference? It's not a function of just these. Is it a function of these three inputs, or does it? There's something nicer about this. Can you guys, can any of you observe what is nicer about this than? No, if I'm making my question clear. So take any Turing machine, the position of a head at time I is a function of what the Turing machine is. It's a function of what time I is. You need to identify which time, and the input you started off with. Once you know these three things, you exactly know where the head is at time I. But for this particular simulation, not this the sort of single tape Turing machine, it has a nicer feature. It's not, notice that the head is just making one sweep this way, one sweep this way. This is how the machine is going back and forth. It really doesn't care. So at a time step t, it doesn't care what the input is. It's just going to go this way, come back this way, go this way, come back this way. So it does kt square and sweeps this way. So this is how the head position is. So the head position in the simulation which we just talked about, simulation above, head position depends only on the length of x, but not x itself. So it needs to know what this n is, because it's going to do tn steps. But it doesn't need to know, when I mean length of x, it needs to know n is the length of x, but not x itself. So these are what we'll call oblivious Turing machines. So oblivious Turing machines are Turing machines where the head position is a function of m I, head position at time I, I and length of input. Length of input x, not the actual input. The only way it depends on the input, not the actual input x. So that's what I mean by. Is that okay? Any questions on this?
So every Turing machine has a sort of oblivious Turing machine that you can simulate the same thing on, right?
Right now, yeah. So no, not no. What we should, I would like to show that we don't know that. What we know is every Turing machine Tn has a single tape Turing machine that is oblivious.
Yeah.
It's oblivious, but it comes at a cost. It comes at a t square n cost. Comes at a t square n cost. So what I will not do in lecture, but what is there in the book is actually there is an oblivious Turing machine which can do it in t log t. The overhead to go from a Turing machine to an oblivious Turing machine is not quadratic. But this is not true for single tape. That is, you should allow the simulator to have multiple tapes. If you allow the simulator to have multiple tapes, then you can simulate it in which it is t square, t log t. Okay. So, and the reason oblivious, will come to it later. We will be using obliviousness later on, and the fact that the Turing machines that we have can be converted to oblivious Turing machines. So what we have seen above is basically any Turing machine, any machine M running in time t, in fact, any k-tape machine running in time t can be simulated by a single tape Turing machine, Tm, which is also single tape Turing. One is single tape. It's single tape. It's oblivious Turing machine in time order k t square. Okay. This is something that's just keep in mind. We will use this later on. This. Notice, so far I've talked about Turing machines which are problem specific. I want to solve a particular problem, I write a Turing machine for it. But typically this is not how we do it. We have a single computer for which the input is not just the problem, it's also the program which we write. So I'm going to want to view as, so I want to talk about Turing machine. So an input, I want to now come up with a different Turing machine, sort of a different Turing machine. Most of these things you would have done in theory of computation, which is sort of what is known as a universal Turing machine. And this is how we are usually dealt with it. You feed it the description of the program and the input to the program, and then this machine runs that particular program which is described by the description of the program on this particular input. So, and why is this feasible? This is because any Turing machine has, the way we described it, has a string description. This is exactly what we did. You can describe a Turing machine. So this is what, in fact, machine M, we described it as K, gamma, Q, delta. So this is a string. So this is a description of the Turing machine. In some sense, it's like the description of the program that you want to run. So that's a description. So you could tell me, I give you this description of the program, and I want to run this program on a particular input. So you could come up with sort of the following thing. You could ask, I want a machine U that takes two inputs, alpha and x. You interpret alpha as the description of a Turing machine, some other Turing machine M, X as the real input, and what you want U of X alpha X to actually is run, this is say M alpha, you actually want it to run M alpha on X. And this is what all computers do. That is, you feed, it takes two inputs. One is the description of the program, and the other is the data of which the program is run. And then you run, the computer runs, the Turing machine runs the program corresponding to the description on the input itself. These are what we'll call Turing machines. So for that, firstly, we want this notion that Turing machines and strings. That is, there's this sort of this one. We saw this already. That is, if I give you a particular, this is the transformation back from Turing machines to strings. So we'll assume, make some conventions over here, some sort of simplifying, which will simplify proofs later on for us. That is, every string corresponds to some Turing machine. By the way, so the notation I'm going to use for this is, if I give you alpha, so let's write this in this. So the notation I'm going to give is, if I give you a Turing machine M, it's corresponding this one. Instead of writing it this way, I'll say this is this string that represents a Turing machine. The book sometimes use this. It uses M. This is just stating that it's a, if this is a Turing machine, this is the string that represents a Turing machine. And if it's a string, what's the other direction? I'm going to say M alpha is the. So this is, I'm going to go back and forth between these two notations this way. So if you have a Turing machine, this is the string representing the Turing machine. If you have a string, this is the Turing machine represented by that string. Say that every string corresponds to some Turing machine. This might not be true. Certain strings are just certain strings, you can't view them as this 4 tuple. What do I mean? Then it just corresponds to the empty Turing machine, the Turing machine which does not accept anything. So that every string for me is in some sense a Turing machine. Every string, some are legal Turing machines, some, if they don't mean anything, if they are gibberish, I will just view this as a Turing machine that does not accept any input. And furthermore, the next one will be the more interesting convention that we'll follow. Every Turing machine is represented by infinitely many strings. Ask why, what's this convention? A Turing machine has just one string represented. What we'll assume is, in the representation of Turing machine, I can just add in states which are unreachable by it. So that's not going to change the Turing machine description, but that's going to be the same Turing machine. It will change the description, but it's the same Turing machine. So, if you're writing programs, like you add a comment to your program, that doesn't change the program. So there are longer and longer strings which all represent the same Turing machine. So we'll make this assumption, and you later on see it. Actually, when we begin diagonalization, we will want a description of a Turing machine which is sufficiently long enough. And that's the reason why I've said this. Every Turing machine has a string representation, and it has infinitely many such string representations. So in particular, there is a long enough representation of this particular Turing machine. These are two simplifying conventions. It seems strange, but we will work with this. Okay. Given this, we'll now go to the notion of universality, which talking about. So what do I want? I want this notion. This is a notion due to Turing, that there is a notion of, there's an universal Turing machine, U, which takes two inputs. This is what we said. One is alpha, which is the description of some Turing machine, of the machine M alpha. X, which is the actual, in some sense, the real input. and U on input alpha x. What I wanted to do is runs the Turing machine M alpha on X. This is what I want to know. But what we try to capture is, I want to say that while it does so without any extra overhead. The overhead is not significantly large. That is, you running it on this should not be any more than what the original machine M alpha itself took on it. And I want to claim that what we have seen so far already proves this. I want to say there exists what I will call a universal Turing machine U, such that for all alpha and x, which are strings, the first thing is whatever we wrote, U alpha x is M alpha x. But furthermore, for all alpha, there exists a constant c, which is just a function of alpha, such that U halts in time, so such that the following, let me write it the other way, so that if M alpha halts in time t on input x, then U halts in time ct log t on input alpha comma x. Yeah, so this is a word full. Let's parse it and see what I have written over here. The first part of it is what we said before. The second part of it states that the universal Turing machine, when it's simulating the Turing machine M alpha, it doesn't take significantly more overhead. If the original machine took t, this takes only t log t. Notice that this constant c could be, this constant c could depend very badly on alpha, but it doesn't depend on x. It's independent of x. So once you fix the machine alpha, once you fix the string alpha, it would have a bad dependence on alpha on the particular Turing machine, but it doesn't depend on input x. X could keep changing, but this c will remain the same. It will be the same c, only t changes as x changes because the length of the input is changing. So any questions on this? This is quite a mouthful of a statement. Any questions on this? Okay. And how do we prove this? What we'll prove in class today, in class, we will only prove, we'll prove a weaker version with ct log t replaced by ct square, using the two claims which we proved earlier in the beginning of the lecture. We won't prove the full strength of the theorem. The book in the first chapter has a proof of this. It's a fairly involved proof. It's interesting, so I'd like you to go look at it. We won't ask you on it, but we'll need the statement of this theorem. So this one, it's an interesting theorem. It's proved by Peppinger Cook and then followed by Peppinger Fisher. And this statement that the overhead is not t square, but can actually be improved to t log t. Okay. How would we prove this? So now I just want to prove that the universal Turing machine, the UTM U, simulates. I had to describe the UTM U. So basically, I need to describe how the UTM performs. The UTM, I'm going to assume, it's going to have it's going to be a single tape Turing machine. It's going to get as input. What is the input? Let's say, what's the input for the UTM? UTM gets an input alpha and x, and it now needs to run this. So how are we going to describe this one? So alpha is the description of some k-tape Turing machine on some alphabet gamma. But notice, alpha could be any such thing, whereas u, because you have fixed u has to have, a priori you have fixed u to have, say, some 10 tapes. U has some 10 tapes. This is its input tape. U has certain number of tapes. So U needs to be able to simulate any Turing machine which possibly has 12 tapes, 100 tapes on it, and U also has a particular alphabet. It needs to be able to simulate a Turing machine which works with a larger alphabet also. So how would one do that? And this, so you notice U needs to simulate M alpha, even if M alpha's number of tapes is greater than number of tapes of U. And gamma of M alpha is not equal to gamma of U. So I must be able to simulate a 15 tape Turing machine on a 10 tape Turing. Because when I say there exists U, you have fixed U. U is not something that changes based on the input alpha. U is one fixed Turing machine. It's some 5 tape Turing machine, 6 tape Turing machine. But yet it must be able to simulate any number of tape Turing machine on it. Do we do that? We just use the claims that we mentioned in the first. We know that you give me alpha, you give me a description of alpha. From that,
if I have a greater number of tapes in M alpha, then I can sort of again stick them parallel in.
So we'll do that, but we'll just resort to the two claims we proved this one. That is from alpha, which is the description of a k-tape Turing machine on with alphabet gamma. We'll use the first claim to go to beta, which is a k-tape Turing machine description with alphabet B. And then we'll convert it to a gamma, which is a single tape Turing machine with a slightly larger alphabet, say B prime. These are the two. This was claim 1, this was claim 2. And this is not a simulation. This takes a description of alpha, converts it to description of B, of this other Turing machine. It takes this one, converts it to another. This is some function just of alpha beta. And now, so what the universal Turing machine does, so it was given alpha and x over here. That's its input tape. So it has alpha. So it copies alpha into its work tapes.
Can I ask a doubt?
Sure.
So what does B dash?
Pardon?
What was B dash?
What does?
What was B dash?
B dash is the alphabet. So we did this transformation from a k-tape Turing machine to a single tape Turing machine.
Yeah.
In that process, the alphabet changed a little bit. If you recall, the alphabet got this. Every alphabet had two things, A and A pattern.
Okay, fine.
So it is if you had started with some alphabet, it goes to a different alphabet. It is the one corresponding to B.
Okay, yeah.
Okay, so it has B. First, what it does, it does some transformation, converts this alpha into a gamma. That's the first thing it does. Then it has the description of gamma in one tape. It's going to write the start state, it's going to write the state of gamma. It's going to write the state of gamma in this tape and then copy the input x onto this tape. So gamma is a description of a single tape Turing machine with a small alphabet on x. This alphabet is going to be the alphabet of the universal Turing machine. So now the Turing machine sort of walks on this tape. It's going to run it's actually going to just do the single tape Turing machine on the fourth tape over here. On this one, it's going to perform all as this one. But each time it has to make a step, it looks up the previous two tapes to find out what is the transition it has to make. How does it have to change things? So that's how it looks it up. And the whole operation goes on within just these. In fact, I think I need only 4 states for this. I need only 4 tapes for these. The one single tape Turing machine, which the one tape to simulate, do the simulation of the single tape Turing machine, one tape to contain. So I will need, so it has only 4 tapes. One is to contain the original input. One is to contain the description of gamma. One is to contain the current state of gamma. And one is actually the single tape simulation which is happening. That's the entire one. So this is actually the universal UTM U is a 4-tape machine. There's a 4-tape machine. You can now once again convert this into a single tape with another quadratic overhead if you want to, but it's a single tape. It's a 4-tape Turing machine with alphabet, say some B prime, that simulates any other Turing machine with at most a quadratic overhead. Okay.
So Prahlad, in claim 1, we went from time t to t log gamma, right?
Yeah.
Then from there, t log, in claim 2, we'll do t log gamma whole square, right?
Yes.
Okay, so you'll have a t square log gamma square, yeah.
Log gamma square. That log gamma square will get swallowed in this. So if you require the universal Turing machine over here, what is this?
That will be the constant C.
All of that will get hidden in the constant C. Those are functions of alpha. There are some functions of alpha. Okay. What I described was CT square. This is what we proved in class now. This can be improved to CT log t, but that's a little far more involved than what I did just now. Okay. Yeah. So all of these were some generic things on Turing machines to say and furthermore, notice this universal Turing machine also has oblivious. It's simulating a oblivious single tape Turing machine. It's oblivious on input X. It depends on input alpha. It's not oblivious on. On the X part of it, it is oblivious. The input alpha, it's not oblivious. So this UTM, the UTM's actions, UTM is oblivious with respect to the input X, not necessarily with respect to the input alpha. You can do that also, but for now I will just ignore this. It's input. Okay. So this is some basic Turing machine things that I needed. Now we'll get back to real complexity. So far we didn't talk about complexity at all. We just had one time parameter and we've been working with it. We'll now get on to defining the classes. We'll first start off with what I want to call efficient computation. I want to define. We'll move to So just recall some of the problems we started off in the first lecture of. We said that some problems were easy. Parity, matching, connectivity, these were problems which we said were easy in the first lecture. And now I want to formally define what it means for this to be. I want to define these are problems, arbitrary problems. So we'll have to both define what it means for these to be problems, what this means, what easy means. We're going to give a formal definition in the next 10-15 minutes or so. Okay. Any questions? Notice that all of these are right now sort of computational problems. What is parity? Parity, you give me an n-bit string, compute the parity. Here the answer was a 0-1 answer. Matching was not such a problem. You're given a bipartite graph and you want to output a matching, a perfect matching. Connectivity is you given two vertices, given a possibly directed or undirected graph and two vertices, two specific vertices, a source and target, and you want to find a path that connects them. So each of these problems are very different. We want to relate these problems. We want to talk of all of them in the same vein. You want to come say whether they are easy, they are hard. But right now they seem to be very different problems. So what we'll work with is actually what are called decision problems, problems which have just 0-1 answers. So far, all of these are problems of the form f going from 0-1 star to 0-1 star. That is, given some input, you want to go to some other input. Whereas now I want to work with decision problems, that is, problems which have just 0-1 answers. That is, f looks like a function from 0-1 star to 0-1. These are also called languages. So language corresponding to this function basically is just the set of all x such that f of x is 1. And the reason is now they're all of, one thing is just to make them all of the same type. They're all Boolean valued functions. Instead of each of them, so that it's easier, it's harder to compare apples versus oranges. Now you have all of them as single problem. So it's nicer to work with this. But on the other hand, so we are going to give me in general, there will be this first step in all of this thing. Given a problem, we will try to find a decision problem. We'll always, to understand how easy or hard it is, we'll find a decision problem that is in some sense equivalent to the problem. This will be problem specific, how you do this. But then when we talk about the problems from now onwards, what we'll be talking about is only the decision version of these problems. We won't be talking about like matching. When I mean matching, what I'll ask is there a matching or not? Not ask, find the matching. So these are, the first one is a decision problem. The next one is sort of a search problem. The connectivity is, I want you to find the path. I'm going to ask you, is there a path or not? The question is, of course, these certainly, if I can do the first problem, I can do the second one. The first is a search question. The second is a decision problem. Question is, can I go from the other? We will, in most settings, we will construct decision versions which are not anymore. That is, you give me an algorithm for the decision problem, I will be able to convert it, use that algorithm to solve the original search problem. We will see instances of this later. Today, I will just work, we'll just assume that we work restricting our class of problems to decision problems, languages. Tomorrow, the next lecture or this one, we will actually see in certain specific cases how to do this. Okay. All of this might be a repetition for some, you would have seen in an early theory of computation class, but let's just do this. So now I'm going to work with, I'm going to restrict attention to decision problems or languages, which we'll also call languages. Okay. That will find. Okay. So now let T be a time constructible function d time tn we'll say this, we're going to define this class, we'll say a language L is in d time tn if there exists a Turing machine M and a constant C such that M is, some people use different words for this, decides or computes L in time C times T for every input. Okay. I find it very hard to write on this iPad. This one, so I'm not being very grammatically correct in my English statements and all. I would expect you to do, I would write, when you write your problem sets or papers, this is not how you should be writing it. Yeah. So, for instance, parity in this language, what was parity? Parity is a Boolean problem. You can see that it is in d time what?
And
It just requires one sweep of the input, d time n. What about connectivity? I had to define what is the Boolean problem of this. So I'm going to define con to be exactly this language version, GST. G is a graph. And there exists a path from S to T. So what is con n?
M, like number of edges.
Number of edges, which, okay, so let's just put an n square bound on it. If you run some DFS or BFS, this is what it's going to take. Okay, and we think of these as sort of efficient computation. Somehow these now, this led to what is called the class P. That is, if these running times, for example, what's another problem? So SAT, you could talk about SAT, which is a phi is a CNF formula. Phi is a satisfiable 3 CNF formula. Say, let's just call it CNF. SAT, what's the algorithm you would, how much time do you, at least the naive algorithm for SAT, how much time does it take?
2 to the n.
So you just go over all possible assignments, so that sort of takes d time 2 to the n. And this is not something which we call which you would consider efficient. And this sort of discrimination, and you would have seen in a algorithms class that matching is also in what, actually I don't recall the exponent for it. It's in d time n to the c for some constant c. This led people to sort of define this class P, which is just the union of all n time d time nc for all constant c's. So this is the class. and they said this is one sort of test of saying a problem is easy. This is you call it easy if there is a polynomial time description, polynomial time algorithm that does it. This is just a candidate. This is, by the way, this is P is sort of used as a surrogate for what we mean by efficient computation. It's one way of so this is an informal term, and it's one way of formalizing this notion of efficiency is P. And this seems to be a good notion sometimes. You can ask, does it capture all notions? That's not true. It doesn't capture everything that we consider efficient. For example, very soon in the course, we'll begin talking about randomized Turing machines, randomized algorithms, and P does not capture those. So this is one attempt to capture notion of efficiency. It's a good attempt. We'll see why it's good, because it has a lot of nice phenomenon going around it. But it is, at least this is one attempt to say that everything in P is what we call efficient. It doesn't capture randomized, and later on we'll see we also do not know if it captures quantum. The other thing is it captures what is called only worst case input analysis. That is, you say something is in P only if every problem has a efficient this one. There might be certain problems which on most inputs actually the algorithm runs fast, on a few inputs it takes very long, but possibly you never care about these inputs. And people, sometimes you might be happy with this notion of efficiency. P is a very strict notion of efficiency. It says every input we want it to run in poly time on every input, which is a very rigid constraint. Whereas actually we only care about it to run efficiently on the inputs we care about. And P does not capture this one. And this is the point we should note. P does not capture. It captures this worst case thing. It says on every input, it says if you say something is not in P, that does not mean that on your particular input, it's not easy. It might be as well have been easy on your input. It's just that there is some input on which this algorithm fails to run in polynomial time. It possibly on all interesting input, it runs in poly time. So that sense. And the last sense I want to say is P does not seem to distinguish between, say, n square and n to the 1,000. Certainly, these are, if you give me an n square algorithm, that's much, much better than giving me an n to the 1,000 algorithm. P sort of is hiding the distinction between these. On a rough level, to talk about easiness, this is okay. But if you really want to care about easy, we need to pinpoint the exponent. And we will do this later on. When we talk about fine-grained complexity, we'll talk. So it's a sort of a coarse notion of efficiency, because these two things, certainly if you give me an n to the 1,000 algorithm, that's not an efficient algorithm, but P is a notion which is sort of saying, for now, I will consider it as a notion. P is saying we'll settle for this for now. Okay. So these are points, I think, to be noted, that when we talk about P as, when we say P is a surrogate for efficient computation, it comes with these caveats. These are the caveats that it comes with. But we will live with this. That in spite of these caveats, why do we work with it? We'll see later on as the course proceeds. This class has several nice features going about it. It's not just this fact that computer is efficient computation. It's a robust class. There are nice reductions that go on between these problems. It's in some sense, you will see that it has various nice features. So we work with this class, even though it has several such drawbacks. These are obvious drawbacks. We will see several more drawbacks as we go on. But yet, it's a nice and interesting class to work with. Any questions? So once we have such a P, we can define the other notion, the X, which is union D time 2 to the n to the C.
Yeah. So
Yeah.
in so D time T of n. So what is n? N.
Oh, n always
So
refers to the input length.
okay, but so you said in the graph example, so input size will also be n square, right?
The
Like
input,
you took.
yeah, that is true. The graph, the input, true. Yeah, so I'm going to be a bit sloppy about these. So you have to, the graph, this one, so strictly speaking, you'll have to describe it in terms of m as, so there, so you're out here, you're bothered about this exponent I put over here, no?
Yeah.
Yeah, so I don't know if DFS runs in time n. It might run slightly more than n. So this input, strictly speaking, refers to the graph description itself, which is already n squared. But this n refers to, one has to be careful about this. I've been sloppy here. In general, when you write it, you should be careful about this. This n right now here refers to the size of the number of vertices, not the actual input length. And you caught me at this. We had to be careful about this while writing it now. So in general, always. So the point is, in general, n always input refers to the input length. When you're working with the specific problems, n might have a nicer meaning, and then you change the notion of n. But when I talk about time n, that's the input length. That's the honest to God input length.
Yeah. Okay.
Yeah. Okay. Okay. So all of this is still in the regime. The x we defined just because I wanted to show SAT. Just state the fact that SAT we were not able to show it's in P. SAT is clearly in X by what we had done, and also it's easy to see P is in X by just whether one. This is all fine. These are all so far what I'm talking about is more like easy problems. What we care about is that there are interesting problems outside P. Interesting problems which we have, which we don't yet, which we do not know are in P yet. I'm not going to write the English sentence to follow what I'm saying. So, and what this course is mostly interested is trying to find out these problems for which we don't have efficient algorithms, try to understand why they don't have efficient algorithms and stuff. So let's go to, the focus of the course is going to be more on that. So let's go try to understand, see some examples of problems which we, examples of problems. Not yet known to be in P. So we already have seen one example. SAT is the example which we have seen all the time. There's a problem which we don't know. I want to understand what this problem is. I'm going to not mention all the problems that we have, but going to mention some of the problems because they're going to have a common feature among them. Another problem is what we'll call the independence, the independent set problem. So this is the language version of it, independent set. So this is the decision version of finding the largest independent set in a given graph. What is an independent set? Independent set is a set of vertices such that there are no edges between any two vertices in that set. And what is the decision problem I'm talking about? Ind set is this particular decision. You're given a graph G and a number K. You're asking there exists an independent set of size at least K. So this is a 0-1 problem. Given an input, you know yes or no to it. This is sort of the decision version of the independent set problem. So this is one problem one. Problem two. Another problem composite. Talk about composite. Yes. I give you a number n. N is in binary, written in binary. Basically, n is not prime. N is not prime. One more problem. TSP. This is once again the decision problem. I'm giving you okay, I'm not going to write this. I'll just say it in words. I'm going to give you a graph, an n vertex node, which all is an n city. It's a graph with n vertices and distances between every pair of nodes. And I'm asking, is there a walk in the graph that goes through all the n cities of size at most k? I give you a graph with a weighted graph and a number k, and asking, is there a walk in the graph which involves all the nodes of length at most k? That's a traveling salesperson problem.
Like, is the graph always complete in
What?
TSP?
What?
Is the graph always complete in TSP?
TSP, yes, the graph is always complete. I'm going to give you n nodes. I'm going to give you every. So TSP is sort of, you have n locations in Bombay. You know how to go from every location to every other location, but there's a time associated with it, and you want to find the way to go from a walk going through every location in Bombay with the least amount of time. So it's a complete graph. It's a complete weighted graph. Of course, you can say that one way of some certain weights are not known. You can just say that those edges are infinite, so large that it's useless to walk along that. So not yeah. So we'll assume without loss of generality that it's a complete graph, but it's a weighted complete graph. Each edge has a different weight on it. Okay.
Yeah.
And these are some problems for which we don't yet know how to solve these things. But one nice thing about all of these problems is, if somebody solves them, somebody solves them, they can convince to you that actually the solution they have satisfies is a yes problem. So the nice thing about them is, whenever all these problems have the feature, all these problems have the nice that when the answer is yes, there is a short proof. Short. Once again, by what do I mean by short? A polynomial sized proof. That proves why the answer is yes. And let's actually go to each of these problems. Satisfiability. Suppose I claim to you the formula is satisfiable. What is the proof? I can give you the proof, which is a satisfying assignment. And this is a proof. Once you have this proof, I can now check if the formula is satisfiable. Given the formula, I do not know how to come up with this satisfying assignment. But once if the formula were in fact satisfiable, there is a short proof that convinces me that in fact the formula is satisfiable. Similarly, independent set. I tell you that this graph has an independent set of size larger than k. What is a short proof that can convince to me that the independent set is size larger than k?
An independent.
So give me
You give an independent set.
Give me an independent set of size k in the graph. All that I now need to check is check that there are no edges between these vertices of the independent set. Okay, more interesting thing is composite. So I tell you now, given a number, it's composite. What is a proof that it is composite?
Give a factor, prime factor.
Give a factor which is not itself. or 1.
Yeah.
And then you need to check. How do you check? You check that actually do the division algorithm and check that it actually formally factors it. So and what's about traveling salesperson problem? I tell you, there is a root of length at most 100. What is the, give me the actual route. Give me the route, and then you just walk along that route, check that every node has been visited, and the length of that route is at most 100. So in each of these cases, these problems, I don't know how to solve them, but whenever the answer is S, it so happens the case that there is a short proof that somebody can convince me that the answer is S. This is not true, by the way, this is one-sided. It's important. Only when the answer is yes, this is the case. When the answer is no, I don't necessarily have the short proof. For example, if you tell me the independent set, there is no independent set of size larger than K. I do not have a short proof. At least I don't see easily how to come up with a short proof that convinces me that there is no independent set of size larger than or equal to K. When the answer is S in each of these cases, it so happens that there is not only is the answer S, but I can convince to you that the answer is S by giving you a short witness or a proof. So these problems, we don't know how to solve them, but yet they have this interesting feature. That is, whenever it's a S instance, whenever in the S case of the problem, you do have a short witness proving to you that the instance is an S instance.
There is a polynomial time algorithm for checking whether a number is prime or not.
Yeah, so this happens. Yeah, so because of that, composite actually is not. So composite is not a problem which is not yet known to be in P. Composite is actually a problem that is in P currently. If I did not know this algorithm, then I would have said it. So I should drop off this fact about it. Composites happens to be like, had we had this class 20 years ago, it would have been a different story. And this is what's going to lead us to. So all these problems have this nice feature. So we're going to put them together. We're going to define a new class and this is going to be the class NP.
So
NP
is in P, right?
What?
Composites is in P, right? You just
composites is in P, but right now this is a composites. So also the way I have defined it, whenever something is composite, there is a short proof to prove to me that it is composite. So what do I mean? I'm going to define this. So L, I'll say, is an NP, or I'm going to abstract out whatever property we saw of these four problems. L is an NP if the following happens. If there exists two polynomials, P and Q, such that P and Q and a Turing machine and a deterministic Turing machine. All Turing machines which we have seen are deterministic, so let's me drop the word deterministic. A Turing machine M, such that if X is in the language, if and only if there exists a short proof. So how short? The proof is not polynomially longer than, it's only polynomially long in terms of the input length, such that M accepts this instance and the witness together, and furthermore, M runs in time at most Q times X. So firstly, the proof should be short, and the time taken to verify that the proof is correct should also be polynomial. Both of these should be necessarily polynomial. Only then will I call, and all the problems which we saw had this feature. So this M is usually called, because it's checking if the thing is called, this M is usually called this M is usually called the verifier. And sometimes it's denoted by V instead of M because it's verifying that the witness W is actually proves to you that the X is in the language or not. So notice that M is not checking if X is in the language. M is checking if W is a witness to X being in the language. M gets two inputs. It needs to check if W is a witness. It's not able to come up with a witness of its own. In all of these cases, I do not know, except for composite. In all of these cases, I don't know how to come up with a polynomial time Turing machine which comes up with a witness of its own. But given a witness, it can check if the witness is actually proves to you that the instance is in the language or not. And notice this is once again one-sided. If X is not in the language, I don't make any claims whether there exists a witness or not. Okay. So much for the definition of NP. Any questions on this?
There's something in the chat, I guess.
No, that's just.
Yeah. So Varun had asked this polynomial time, the sum product composition. We will see this. There are other smaller classes which also have this. So polynomial time has the fact that you can do composition. There is a polynomial of a. What does it mean composition? We'll come to this shortly. Once you come to reductions, this will be clear. To answer Varun's question, to even formally state Varun's question, I will need the notion of a reduction. Because that will be the next thing, but I don't think I have time to come to it. So I have just about 5 minutes more. So I will do something else which I want to do. So, and I'll talk about this alternate. So NP, so right now the way I defined NP was in terms of this efficient verifier. But NP, historically, this was not how NP was defined. NP was defined in terms of what are called non-deterministic Turing machines. So what's a non-deterministic Turing machine? A non-deterministic Turing machine is similar to the Turing machine which we talked about, except that at every time step, so previous, what was delta? Delta was a function that went from Q cross gamma k to Q cross gamma k minus 1. If it were a k-tape Turing machine, a single tape, it will be gamma itself. And yes, okay. This was what it did. At every step, it tells you deterministically what is the next step to take. So if you look at this, it tells you a non-deterministic Turing machine this is no longer going to be a fixed step. That is, there will be two options to take at every point of time. That is, so there will be two functions. There will be, say, what I'll call delta 0 of this type. There will be two transition functions, delta 0 and delta 1. And the non-deterministic Turing machine at every step can either decide to do the transition rule according to delta 0 or according to delta 1. It gets to choose whichever one it wants to. It gets to choose this. So what's happening? So in a deterministic Turing machine, you start with a particular initial configuration. It tells you how to go the next step. Then you can go the next step. Then you can go the next step. There's only one route all the way. Either this route continues infinitely if the machine doesn't halt, or at some place the machine halts and it stops. That's the deterministic, how the deterministic Turing machine functions. A non-deterministic Turing machine, on the other hand, At every step, it has two possibilities. It can take either this step, either follow the first transition function or the second transition function. And once again, at every step, it sort of branches out. It has this sort of branching out feature. And once again, this can either go on infinitely, or some of the branches will halt at some location. Some branches might go on this one. What does so if I say this, say at utmost Tn, I want to, so the non-deterministic Turing, I will say that L belongs to non-deterministic Tn if there exists a non-deterministic Turing machine M such that for every X in the language, there exists at least one path, one of these paths that stops within time Tn and says accept. I don't care, all paths accept. At least one path should tell me that it accepts. There exists a path that causes the machine to accept within T time steps. If X does not belong in the language, actually this is if and only if X doesn't belong in the palette, there is no path that halts within T's time steps. So in particular, once it crosses T time step, you could just halt and say reject, because I don't count it as accept at all. You could assume that it doesn't go infinitely, it stops at T, it just all of these halt. You could assume all of them halt, some of them possibly accept, some of them reject. But n-time non-deterministic Turing machine is you have multiple paths, multiple parallel paths going. All I care is there one path that causes the machine to accept. It's a deterministic Turing machine. It's like a deterministic Turing machine, except that it has two transition functions and it gets to choose. It's not tossing random coins or anything to do this one. It can get to choose at any point which one to do. It's an arbitrary guess that it makes. Even if there's one guess that causes it to accept, you say the machine accepts it. If all the guesses cause it to reject, only then will you say the machine rejects the input. That okay? And NP is what I want to say is the following. I want to write down, I want to make the following proposition, that we have defined NP in two different ways. So NP, the way we defined it earlier, is exactly the same as this definition. And why is this true? Let's just observe it and then we'll wrap up for the day. So I gave you one definition. The way we defined the NP was not in terms of non-determinism. The way we defined NP was in terms of, this definition is in terms of verifiers.
This path is the proof that verifier is verifying.
Yeah, so we have to prove both directions. So what you say is the path. So if there is a path that causes it to accept, certainly that path is what I can give it as the witness.
Yes, yes.
So that shows this that the right hand side is a subset of the left hand side. That is, everything which is in n time n to the c is actually in NP, because that path is at most polynomially long, and hence that can be given as the witness. Okay, so that shows one direction. What about the other direction? Why is NP in? Give me any language in NP. That is, there is a verifier. I want to say that there is a non-deterministic Turing machine that accepts it.
use the same path to
There is no path right now. There is no path. It's just a verifier and
the U which was given for the verifier.
yeah.
You can use it as a path in some way.
So what you're going to do is you're going to do this. You come up with you have only one transition function corresponding to M. So we have NPs in, there's only one transition function. You're given a language in NP, and that tells you this one. Now from that, you need to come up with a non-deterministic Turing machine. So how do you come up with this? You don't have access to W. So each time it has to read a bit of W, it makes a non-deterministic, it decides whether W is 0 or W is 1. And those are the two different transition functions. That is, it sort of, give me a transition function, it breaks it off into two transition functions depending on whether the ith bit it reads is going to be this, or if it's going to read this particular, so it's basically going to run this particular machine. It's going to be exactly as this machine M, but it doesn't have input W. So whenever the machine W is going to read a particular input, the ith bit of W, it decides to do one of the two things. It either reads it as 0 and goes along one way, or reads it at 1 and goes the other way. So it branches at every step. The transition function breaks off into 2, and that's the whole this one. So that's how NP is this one. If you stare at it, this is an obvious connection. Historically, NP was defined in terms of non-determinism, but it'll be easy for us to work with the verifier definition, and we'll stick to the verifier definition almost completely in this course. Very rarely will we ever go to the non-deterministic definition, except possibly when we're talking about the time hierarchy or this one. There we'll talk about the non-deterministic. Otherwise, the verifier definition is a very clean definition, and we'll work with that definition for the most part of this lecture. So what we'll do next time will be, we'll define that show that this class we'll define the notion of reduction. And this class will have some very nice complete problems based on these reductions. What's going wrong with my pen? Which will lead us to the Cook-Levin theorem. And we'll see some more properties of NP. Let's stop with this. Any questions?
So if we define another type of Turing machine in which there are more than two transition functions.
Yes.
Will it be equivalent? So can this Turing machine be simulated by the two transition function Turing machine?
Your basically question is, can I have the branching factor, if it's of 2, can I make it 3 or 4 or 5, whatever? And this is this one. That is basically you can simulate a branching factor, for example, a branching factor of 4, you can simulate with 2 steps of branching factors of 2. Therefore, 2 is sufficient. 2 is sufficient. Once you have 2, you will be able to simulate all of them. Whether you do 3 or 4 or this one, it really doesn't matter. That will just, it's the same sort of, if it's 3, the depth will increase by a factor of log 3 to the base 2. A logarithmic factor. That's a constant factor. Anyhow, when we say n times n to the power c, we are saying it. Actually, this is when I meant this, I meant c times this. I'm going to always allow a constant overhead in the definition. D times Tn doesn't mean it accepts in Tn. It accepts in any constant times Tn. Yeah. So, so 2 is sufficient. Any other constant can be simulated using 2.
Yeah. Okay.
Any other questions? Okay, then we wind up. By the way, problem set, the first problem set will be out in a couple of hours. It's due in 2 weeks from now. So those who are planning to credit the course, please go ahead and do it. Even others, it'll be a very good exercise to get your hands dirty. There are a lot of interesting properties of NP and NP completeness and reductions in the problem set. So I would advise you, even if you're not submitting it to me, to actually look at the problem set and attempt the problems. Okay.
So maybe I'll also just add that the problem set actually will involve things that we will see through the course of the problem set. So your deadline will be in March 3rd or something, but there'll be some questions which involve concepts that you haven't seen yet, but there'll be some questions that you can solve right away. So it's also a good idea to start thinking about these questions when the next couple of lectures happen, and so on. Yeah,
we haven't covered all the material for the problem set by today. It'll involve, I think it'll involve some things which are covered next Monday, hopefully everything by Monday. If not, a little bit might overflow to Wednesday. Okay.